So the question I'm going to be looking at today is the question 7.1 in the book. It's where we put a delta function in the center of an infinite square well. H prime is equal to alpha delta function times x minus a over 2. And look at the first order corrections to energy that must be made. So the first order correction to energy is given by this equation over here, which you can find in your book. En is equal to bracket sine 0 h prime sine 0. First step, once we have this written down, it's then write into integral notation, subbing in h's and phi's. So what is this going to look like? First thing we're going to do is we're going to write our integral down from 0 to infinity. We're going to use our sines from the infinite square well. What does this look like? It looks like square root of 2 over a sine of pi n x over a times our potential minus a over 2, and then the next sign 2 over a pi n x over a. Next thing we're going to do is we're going to pull out some constants and make some simplifications. This is, we're not actually evaluating the integral yet, we're just making simplifications at this point. Pulling stuff out so it looks nicer. We're going to pull a 2 over a out, an alpha out, and we're going to combine our signs of n pi x over a. And we have to leave in the delta function and this x minus a over 2 term. Now we can actually evaluate this. So what does this evaluate to? The evaluation of this integral is actually pretty simple. We're going to be left with a 2 over a alpha times our sine squared. And we're going to be left with this n pi over a times a over 2. And this is going to be our correction to the energy. So I'm going to bring this up here just to make it look a little bit nicer, and so we can do a little bit more work with it. So our E1 is going to be looking like, well, it's technically on E1. So our first order correction, En, is going to be equal to this 2 over a alpha sine squared of n pi over 2. And now, what does this tell us about energy? What this tells us is that for even solutions of this, where n is equal to, say, 2, 3, 4, 5, 6, 7, blah, 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 we're going to have one set of solutions, and for odd, we're going to have a different set of solutions. So, if we have n equal to an even number, so if n is equal to even, we immediately know that En is equal to 0. And if n is equal to an odd number, then we know that En is going to go as 2 over a alpha. And the last part of part A that the book wants us to explain is it asks us for why the energies are not perturbed for even n. And what we can see here is that when our function's even, essentially our potential doesn't feel the perturbation that's acting on it. And that's why we essentially don't see a perturbation for even n. I'm now going to pause the video and I'm going to solve part B.